Okay, so hi, welcome to the session about cryptography. I'm Neil Bitansky, and we have a pretty diverse session, and I'll start with some ranting. So the first paper is about affine determinant programs, a framework for obfuscation and witness encryption. And you may have heard about obfuscation. This is basically the task of taking a program and rewriting it so that it hides the implementation details. And this is something very powerful. We consider it the holy grail. In crypto, we can do a lot from obfuscation, essentially anything. And in recent years, we've even seen notions that have no lower bounds whatsoever, so they may be feasible. But at least at this point, it's sort of still a flying pig. We not really know whether we'll ever be able to sort of like base it on standard assumptions. But over the past 5 years, we've seen like an immense effort of sort of bringing this thing down to earth, basing it on plausible assumptions. And then this line of work can roughly be divided into two main directions, where one is sort of like reducing this primitive to a new algebraic object called multilinear maps, and the other one is to new notions of pseudo-randomness. And we'd like to have more. In particular, at least the first one, multilinear maps, sort of ended up being a broken pig. It's not quite dead yet, but we haven't really succeeded in doing this under reasonable assumptions. The that direction is very much alive, and hopefully we'll be able to base it on sort of well-studied assumptions eventually. And this work here sort of tries to add another direction, another object that we can try and base obfuscation on, and this is an object called affine determinants. So I should say that all of these works are really still not there, but there is much progress. So basically, we've reduced the problem from flying pigs to jumping pigs, perhaps. And even though the assumptions that are used here may seem speculative and quite strong, and often they actually break, then I want to say that this is sort of like a natural part of the cryptographic process. This is something that we have to do in order to advance our science. So keep an open mind and try to break these things. It's a win-win. We'll learn something anyhow. Okay, so the second paper is about something called a decomposable randomized encoding. And this is basically a way to re-encode a function. So you take any function that you can think of and find a way to encode it using randomness. And this encoding should have the following properties. So first, we want to say that the output of the encoding leaks no information but the original output of the function. It's sort of hiding. And second, and the reason you can just give the output as the encoding, is that this encoding function should be much simpler in some sense. And specifically, we want to be very local in the input. So each output bit of this encoding depends only on a single bit of the input. It can depend arbitrarily on the randomness. And this simplicity in the dependence on the encoding is regardless of how complex the original function was. And some of you may know this object as Yau's garbled circuit. And as you may know, it had like an immense impact on crypto, especially on multi-party computation. We really use it everywhere. And what this work is concerned with is how much, how big should this randomized encoding be in terms of the input? Can it be sort of linear, as in this picture, or does it have to be larger? And here we don't know pretty much anything. And this work proves quite general lower bounds. And interestingly, it does this using Nechipork complexity, which is something we heard about in the previous session. I think that a nice lesson of this is that, looking at old papers could really pay off. So looking forward to hearing about this. The third paper is about cryptography from information loss, and it's really about reductions, which are sort of the bread and butter of cryptography, and complexity in general. We'd like to understand everything that there is to understand about them. And one thing that people have looked at is these reductions are sort of instance compressing, where you can take an instance for one problem and sort of reduce it to an instance for another problem while preserving membership, but while reducing size. And this is something that we also know from parameterized complexity. It's called kernelization. And it's also known to have some cryptographic implications. And this work sort of generalizes it, I think in a very natural way. So they consider reductions that are sort of lossy. So this means that we don't necessarily compress the instance, but we lose a lot of information about the instance. The new instance sort of leaks a little bit of information about the original instance. And this really generalizes the previous notion, and also other notions that we have in cryptography or in general, like worst case to average case reduction, that sort of lose everything about the input. You go from one worst case input to a fixed reduction that is completely independent of this input. And the question that they ask is a pretty natural one, is when do such reductions actually imply cryptography? Okay, one-way functions, perhaps even more. What are sort of the conditions that should be satisfied to show something like this? And we give a pretty comprehensive answer, and one of the things that I like about it is that it sort of unifies many of the previous results that we had here. Okay. So the next talk is about the cryptographic hardness of local search, and I'm going to be ranting about this more later, so I'll save you the trouble now. And I'll move to the next one, which is computationally data-independent memory hard functions. And memory hard functions are basically functions where you have to invest a lot of space in order to compute them, and not just a lot of space, but also a lot of space in an amortized sense over time. And this is something that has been extremely useful. It's actually used in the real world, both for password hashings, also in blockchains, where the goal is to sort of avoid a situation where sort of designated hardware can significantly reduce cost in attacking these cryptographic primitives. And it's a very nice case where we have a beautiful theory that very fast translates to real-world applications. And something that matters a lot in these real-world applications is sort of the exact memory hardness of these functions. And here something that sort of is true today is that the best functions in terms of their memory hardness are sort of vulnerable to side channel attacks. There are better functions that are called data-independent hash functions that are more resilient. And what this work shows is that you can sort of have the best of both worlds, both resist side channel attacks, leakage on the function evaluation, and yet have optimal memory hardness. And it's really, I think, a great ITCS work. It sort of involves innovative definitions and techniques, combines things quite nicely. Okay, so the last talk of the session is on separating two-round secure computation from oblivious transfer. Rather than ranting on the paper, let me tell you a real-life story. So there are 5 authors on this paper, and unfortunately, none of them could come. And Sanjem was actually supposed to give the talk, and he has a lovely house in Berkeley. And unfortunately, recently, due to a storm, his roof sort of flew off. Yeah, this is pretty grim. So now we have a roofless cryptographer in Berkeley. And by roofless, I mean without a roof. He's actually a kind person. So if you live in the area and you're into construction, so give him a call. So there's also an actual paper, a nice one, and Sanjem's student James will tell us about it, and I'm sure he'll do a better job than I am. So without further ado, let's proceed to the talks. Okay. And our first talk is going to be by James, right, who is going to talk about these affine determinant programs.
Okay. Yeah. So this is joint work with Yuval, Aayush, Fermi, Amit, and Mark. And yeah, as Nir mentioned, this is going to be a talk about program obfuscation, where we start with a computer program P, and we want to apply some obfuscator O to it to produce an obfuscated version of the program. And intuitively, what we want O to do is we want it to scramble the implementation details of the program while maintaining its functionality. So an evaluator that has O of P in its possession can use it just like P, but hopefully not learn any details about how P was actually implemented. And so there are some various security definitions related to program obfuscation. And one we're interested in is indistinguishability obfuscation, which stipulates that for any 2 programs that compute exactly the same function, that their obfuscations will be computationally indistinguishable. Yep. And so this is again, as Nir mentioned, is a very important primitive, and it has been termed a central hub of cryptography just because it implies so many cryptographic primitives. And indeed, it is a central open question in cryptography, like whether or how to build an obfuscator that can be based on a standard assumption, which we don't achieve in this work. But so yeah, one more fact before I go on is that this original this paper of Garg et al. In 2013 that gave the first plausible candidate for I/O. Also showed that like if you have I/O for NC1 for logged up circuits and you have fully homomorphic encryption, then this implies an I/O for all polynomial size circuits. So we'll just focus on I/O for NC1 from now on. So I'll give an overview of pretty much all the existing approaches that have been taken by members of the community to try to build I/O. So the first is this original approach that was started in the work of Garg et al. So they first invoked Barrington's theorem, which says that any logged up circuit can be written as a constant width polynomial length branching program. And then they basically apply some randomization, some cryptographic compilers to the branching program, and take advantage of the extra structure in a branching program to try to obfuscate this. So another approach is just to not even go to branching programs, just try to obfuscate the circuit directly, kind of maybe randomize each gate and tie everything together with a multilinear map. And thirdly, it was shown in 2015 that this primitive called functional encryption actually implies I/O. So a third approach is to try to build functional encryption. So I'll explain some issues with these approaches, starting with this multilinear map, right? So a multilinear map is a very strong cryptographic primitive. And it basically allows you to compute a polynomial over encrypted data and then test whether the resulting encryption is 0 or not. So this first step is basically like fully homomorphic encryption, but the second like 0 testing step makes this a stronger primitive. And while there are some known candidates, they are all pretty complicated and inefficient, and they also, even worse, like they suffer from various attacks, and the security of them is still pretty poorly understood. So this third approach, it turns out that this FE to IO transformation is actually, it's non-black box, and it adds like a pretty major efficiency overhead. So while this approach is promising, it doesn't appear to, like, any time in the near future, it doesn't appear to lead to any like concretely efficient constructions. And even functional encryption itself is pretty hard to construct. Known constructions are based on either multilinear maps, which we want to avoid, or recently some new pseudo-randomness assumptions that are still being better understood. So this work, we're going to go back to the original Garg et al. Approach, tweak it, and really like use as our guiding principles simplicity and like a hope for concrete efficiency. Okay. So this approach can really be abstracted into like a two-step process. So first, recall that we're starting with a branching program. The first step is to compute some randomized encoding of a branching program. And randomized encoding is basically like a randomized representation of the branching program with respect to some input x, such that like that representation only contains information about like the branching program evaluated on x and nothing else. So just this like encoding basically gives this notion of one-time security that allows the evaluator to evaluate your branching program on one input and not learn anything else. So of course, to achieve obfuscation, we'll need to allow the evaluator to evaluate on any input of its choice. So this second step is to kind of like, how do we add some more randomness or some more cryptography to this randomized encoding to upgrade it to many times security and allow the evaluator to evaluate on any input of its choice while still preserving the security properties that we want. Pretty much, yeah, like all the works that I listed on the last slide that follow this approach have in their first step, they've used this thing called a Killian randomized matrix branching program as their randomized encoding. And then, unfortunately, in the second step, they, or most of them, end up encoding it in a multilinear map. And there are good reasons why they do this, because the structure of the matrix branching program actually, it introduces like a lot of potential attacks when you want to hope for many times security that seem to require some like strong like cryptographic steps in the second step to defend against. And if you're familiar, in particular, this is like mixed input attacks or partial input attacks. So I mean, having said that, there's actually one exception that I'm aware of that attempts to do step 2 without a multilinear map, but they end up with some pretty complicated construction, and we want to be really stressing simplicity in our work. So our main idea really is to just go back and replace the first step of this two-step process. So instead of using the matrix branching program, randomized encoding, we'll use a different randomized encoding that was introduced by Ishai and Kushelevitz in 2000 in the context of MPC, and we call it an affine determinant program. Okay, so what is this? It's an encoding. So we take some binary function f, and you can encode it into n+1 square matrices over some large field fq. And then to evaluate on some input x, first you take an affine combination of these matrices. So you take A, and add a subset sum of the BIs corresponding to your input x to produce your matrix mx, and then you just take the determinant of mx, and this is going to be equal to f of x. So in particular, this should be 0 or 1 on a binary input x. So this is the encoding, and in 2000, Ishai and Kuchelevich showed how any branching program can actually be written as a polynomial size ADP of this form. And beyond that, they show a technique for re-randomizing this thing to get like this one-time security that I talked about. So how to do this is you basically just take a uniformly random matrix R and S, and like right and left multiply all of these matrices A and BIs by R and S. And if we call these like the hat matrices, everything remains the same. And then you can show that like m hat of x leaks nothing about your underlying branching program at all, except for the value of the branching program evaluated on x. Okay. So basically, like if you just have in your possession this m hat of x, this is kind of like this is your randomized encoding. It gives you the ability to evaluate on the one input x. But to achieve obfuscation, right, we'll have to give the evaluator all of these matrices so they can evaluate at any input of their choice. So like what kind of security can we get from this? So one thing to note is like actually one issue that this doesn't have that matrix branching programs do is that there's not really a notion of a mixed input attack, right? Because there's just one matrix here per input bit. Okay, so that's our first step, and then basically we show like some general recipe for how to implement the second step that crucially does not rely on multilinear maps, and we try to keep these steps like simple and elementary. And I won't have time to get into exactly what we do, but there's like I do want to mention there's just like a whole space of like of different transformations you could try, and like it's very like we start exploring it, but there's like much to be done, I think. So basically what's in the paper beyond what I talked about is so this generic recipe which we instantiate to give one IO candidate, and we also explore like ADPs. We do some sort of general exploration of ADPs and like generalize them, like we give a more general version definition of them than what was on the slide a couple slides ago. And we include a very simple witness encryption candidate. Okay, so it's very simple. It's not based on multilinear maps. It just uses some simple linear algebra. It fits into like half a page. So I'd really like encourage anyone to like look at it and try to cryptanalyze it. So the bulk of our paper is like cryptanalysis, basically motivating our decisions and the techniques we use to randomize these things. But I do want to stress, like, I think the main contribution of this paper really is just the new approach. So we basically spell out a new approach to getting I/O that doesn't use multilinear maps, and we think this like lends itself to some pretty simple and efficient candidates as compared to the other approach of based on matrix branching programs. And so because of this, we have some really like pretty elementary constructions that anyone from the community can look at and try to cryptanalyze, and we really encourage this. In particular, like our candidates don't rely on like multilinear maps or functional encryption, so there's a very like low barrier to entry for people to look at these things. And so with that, I will end. Thanks.
Any questions to James? Yeah, Thomas.
So you didn't say, or maybe I missed it, is there a way to state the assumption that you're making that underlies the scheme so that you can extract it?
Yeah, so we don't have like a simple assumption that this reduces to, and that's a thing we want to keep exploring. So far, like basically what we've done and our candidates are just motivated by the cryptanalysis we've done. So yeah, it would be great if we could reduce to some simple assumption, but that's not the case right now.
Okay, so let's thank James again. And next, Marshall is going to tell us about the complexity of decomposable randomized encodings.
So yes, this is joint work with Justin, Tianren, and Tal, who are in the audience, as well as Yuval Ishai, who's not here. So secure multi-party computation. For those of you who are not familiar, this is a primitive that allows a number of parties to jointly evaluate a function on their inputs and maintain some notion of privacy on their inputs. Canonical sort of example of this from the 80s is Yao's millionaires problem. This is a specific function. So you have a bunch of millionaires. They don't want to tell each other how rich they are, but they want to learn who is the richest. So they want to learn who's the richest, but they don't want to learn anyone else to learn anything about them. And today, so secure multi-party computation is very popular because it allows you to run blind auctions and stuff like this. But we suffer from this new problem that it's really expensive. So right, there's always this trivial protocol which, if you don't care about privacy, where you send the inputs and evaluate the function, and all of our multi-party computation protocols tend to be much more expensive than this, in practice at least, than this silly solution. And so this work is looking at sort of is there some inherent cost to privacy here? And in general, there's not really hope of getting any traction, so we're looking in particular at the communication cost of non-interactive protocols. Okay, so our setting, decomposable randomized encodings, what are they? So you have n parties, this is what we're going to think of, n parties in this special bottom party who's a referee, okay? And some angel comes and delivers them a random string. Then they receive a bit, 1 bit each, and they send a message to the referee. The referee should be able to evaluate some function f. This protocol is designed to compute this function f, so you can get some y. And so that's a correctness guarantee, and we want the security guarantee that he shouldn't learn anything else. Okay, and how do we formalize this? Generally, there's some simulator that only takes as input y. There's no x's here at all. Just takes this output and can simulate the view of this referee. Okay, so this in particular, for those who know what these things are, this captures actually garbled circuits, even though the way I've described it looks very different. But these are a core ingredient of many practical MPC protocols that are being run today, and the size complexity is the major bottleneck there. Okay, so our question is, how long do these DREs need to be? And our answer is, they need to be nearly quadratic for many functions. Okay, and in particular, we can point to specific examples. So just as a baseline, right, if we don't care about privacy, these n parties could just send their bits to the evaluator, and this has a cost of n. Okay, so we have a pretty big gap here. Prior to this work, no lower bounds, only linear lower bounds were known. And in particular, there were no superlinear lower bounds, even if there were no counting arguments. Nothing was known, basically, here. And in general, if you want to compute general functions, the best, at least in the statistical setting, the best upper bounds are exponential. Right, and so we also show upper bounds that are nearly matching for some specific functions in this class of functions for which we have lower bounds. In particular, we give, and what's most interesting is we give a candidate PRF that has nearly optimal DRE size. And so PRF garbling is like sort of a target in many of these works. Okay, I'll say more about that later. So how does this lower bound go? So let's do the following thought experiment. So the parties get their random string, and this random string, depending on whether they have a 0 or a 1, will define 2 messages, okay, for every single party. And what we're going to look at is we're going to look at this big joint distribution over these messages, okay? No longer fixing the randomness. So this is distribution over all of this message space. And the first step is we're going to pick some special subset of blue parties, just the first couple parties, let's say. And we're going to consider what happens if these special parties send both of their messages, and all the rest of the parties only send 1. Okay? So now, from the correctness property, we can observe that the referee can evaluate this residual function where the bits that aren't corresponding to special parties are sort of hard-coded, this restricted function. And this allows him to, he can evaluate this on all points for the special parties, and this allows him to reconstruct this large vector. And this vector could potentially contain a lot of information if this function f admits many distinct subfunctions. Okay, and I'll return to this later about f, but let's just keep going. Assume that this f has this property, so there is a lot of information there. Then, second, we can observe from the security property that if we only look at these non-special messages, because he was only getting one, by the security of this protocol, they shouldn't contain any information. And so what we can conclude is that these special messages, this blue portion, must encode a lot of information, and particularly these messages must be very long. Okay? And then the next step is to just repeat. We just move on. We define the next set as special, and iteratively we prove that everything has to be very long, or almost everything, depending on the function. Okay, and so if you plug in parameters, you get then this sort of, if we take log n block sizes, assuming that our function has this property, then each log n block must encode n bits, and if you do the math, you get n squared over log n. This is the message. The messages need to be collectively at least this long. Okay, so what functions, the question remains, what functions admit many subfunctions? And you've already seen it in the last session. This is exactly this sort of, these functions that are amenable to this Nechiporek method. Okay, I'm not going to reiterate what they are, but I'll just give you some examples. So right, as we heard earlier, distinct elements, this problem where you're given m integers of size at most m squared, you have to put 1 if they're all distinct, 0 otherwise. This admits many subfunctions and gives you this nearly quadratic lower bound. In particular, we also show that it admits, this function admits a slightly superquadratic upper bound in the DRE setting. Random functions, as you might expect, have a large Nechiporek complexity. Correspondingly, exponentially strong pseudo-random functions, which I'll say more about in a second, also have nearly quadratic DRE size. In contrast, for those who are aware of what this is, weak PRFs, there is a weak PRF candidate that was introduced last year by Bonnet and others that has strictly linear size. So this gives you a fairly large gap between weak PRFs, but I'm not going to tell you what that is if you don't know. And there's many more examples of functions like this from the sort of other lower bound literature. Okay, so next I want to tell you briefly about strong PRFs, and particularly this candidate that we have that is optimally garbleable and why you should care. So, right, just to review, what is a pseudorandom function? What is a PRF? So we say a pseudorandom function, it's this keyed function on n bits with Boolean output. If any exponential time here, 2 to the n over 10 is sort of arbitrary, distinguisher can't is given oracle access to this keyed function where the key is randomly chosen versus a truly random function, and he can't distinguish between these two settings. So this is a exponentially strong PRF. And why do we care about pseudorandom functions in this DRE setting in particular? Well, here's a slide. There's lots of citations. As you can see, you should care about it because other people do. But they tend to be very useful for applications in searchable encryption and secure keyword search and many other things. So this is why it's very important to get the size of these objects down. Right. So what is our candidate? So our starting point is this thing called the hidden shift problem. So in the hidden shift problem, you're given oracle access to this function, f sub k, which basically, it computes the Legendre symbol. So it outputs 1 if k plus x is square and 0 otherwise in this ring ZP, where p is large. And the goal of this hidden shift problem is to recover k. Okay, so this has been relatively well studied in the mathematical community. And in particular, some various groups have conjectured that this is indeed a polynomially secure PRF. Unfortunately, it admits efficient quantum algorithms and actually a sub-exponential classical attack modulo an assumption on smooth primes. So it won't give us it doesn't yield a strong lower bound. But instead, we make a very small modification to this function that I described earlier. We just restrict the input domain. Okay? Just restrict it to 0 to 2 to the n minus 1, the first 2 to the n inputs. First, what I guess isn't really well defined here, but you know what I mean. And this surprisingly seems to, this simple transformation breaks all known existing attacks. All the existing attacks crucially rely on the fact that you can evaluate the function everywhere. So yeah, just to summarize, we have nearly quadratic lower bounds for distinct elements in PRFs, matching upper bounds for the same functions. And so what is open? So the hope of proving super quadratic lower bounds would be great, but it seems unlikely due to natural proof barriers. So either you need new ideas, or you need to, or please break this PRF candidate. Another interesting direction is subquadratic bounds. So there are very interesting functions which aren't sort of amenable to our technique. So for example, the OR function, there's a DRE for OR that's a very simple DRE for OR with size n log n. And we believe this is n log n is needed, but we haven't been able to show it. Majority, we don't have a better upper bound than n squared actually. So it is this tight. And again, even for distinct elements, we have a polylog gap here. And so if you could close that, it would be great. Yeah, that's it. Thanks.
Questions to Marshall? Yeah.
Encoding these DREs, are they all related to like secret sharing schemes?
Yes, there is a connection. So one route, in fact, to maybe answering some of these questions is through lower bounds on secret sharing size. But yeah, there's a very closely related primitive called conditional disclosure of secrets.
Right.
Yeah.
They're using the upper bounds, right?
Yes.
More questions? Okay, so let's thank Marshall again. And the next talk is going to be about cryptography from information loss, and Prashant will be giving the talk.
I would like to start by claiming the prize for the paper with the most number of authors in the conference. So crypto, right? So crypto is basically hardness with structure. To do anything in cryptography, to construct anything from the most complicated primitives to the simplest of primitives, you need a hard problem with some sufficient structure, right? And what does this mean? Well, hardness is rather simple, right? There are only so many different kinds of hardness. There's worst case, average case, maybe a few more things, but it's easy to tell you what kind of hardness I mean. But structure is more complicated. Like there are many different kinds of structures. Maybe a problem has algebraic structure. Maybe it's sparse, right? There are many possibilities, many dimensions. And the question that we are interested in our work is what kind of structure is sufficient, and what kind of structure is sufficient to put together with hardness to get cryptography, right? And lots of people have asked this question in the past, and we have a set of answers for different kinds of hardness. Like we know that if we have a problem that, for example, is average case hard and has statistical zero knowledge proofs, then we know that you can construct one-way functions with this, right? We know a bunch of other answers, but this is the one that I want you to keep in mind. It's going to show up later. And what we do is we give a couple of new answers to this question, right? We show that a certain kind of what we call lossy reductions that I'll tell you about in a minute is sufficient structure to use with worst case hardness to construct one-way functions. And also that certain stronger reductions that we call compressing reductions are sufficient to construct collision-resistant hash functions from something a little more than average case hardness, right? So what are these lossy and compressing reductions? Well, you have a reduction, right? A reduction is like a randomized algorithm which reduces one problem to another, one language to another, and has some errors, say like a small constant error. A compressing reduction is one which compresses its input. So it gets an input of size n. Maybe it's the number of bits in the input, or maybe it's some other parameter of size, right? And its output is smaller than some t of n for some function t. Think of t as some sublinear functions for now. This is a compressing reduction. A lossy reduction is a generalization of a compressing reduction, where you say that you allow the reduction to output many bits. Maybe the output is even longer than its input. But what you ask is that it loses information about the input. And the way we ask for this is we say that you take any distribution over inputs of size n and look at the mutual information between the output of the reduction on this distribution and the distribution and the random variable itself. And we say that this mutual information has to be less than t of n. In particular, note that any compressing reduction is going to be lossy with the same t, but the other way around may not be true, right? And these reductions are related to lots of other things that show up in a lot of different parts of computer science. One example is kernelization, which is like a central thing in parameterized complexity, where the idea is that you reduce a problem to a problem that is smaller in terms of some parameter. Right? And then there are instance compressing reductions, where you try to reduce a problem down to its witness length, which are interesting. And there are a bunch of other notions that are similar, where you ask for reductions to some different functions of the input and so on. On the other side, in cryptography, there are these things called randomized encodings, which were mentioned in both of the previous talks, right? Which are actually a special case of these lossy reductions with some additional properties. So you typically require some additional properties, but you can think of lossy reductions as a generalization in one direction of randomized encodings. And similarly, they are a generalization of certain kinds of simple worst case to average case reductions. Right? So these kinds of things show up everywhere. They're quite common. And in fact, they have even been studied in the context of cryptography in the past, for certain kinds of composite languages, right? In particular, consider a composite language which is constructed like this, okay? You take any language L and consider the composition with OR, right? Where you say, okay, the OR of L is like the language which has this tuple of inputs of length n, and you ask whether there exists at least one of these that is contained in the language. So this is a composite language. And it was noticed by Handike and Nauer a few years ago that if you have certain kinds of compressing reductions for the OR of SAT, then you can use that to do some surprising things in cryptography. Right? They showed that you can use this to construct collision resistance from one-way functions, which we know you cannot do it in the black box way, and it would be very surprising. And this was very nice until not very long after, Fortnow and Sandhanam said, well, seems like this is too good to be true. In fact, such reductions would actually imply something much more serious than this, that the polynomial hierarchy would collapse. And this was followed by work by Drucker, who showed something considerably stronger. Right? He said, okay, so you don't need to restrict yourself to these kind of errorless instance compressing reductions. You can in fact relax your reduction to have some error, and it doesn't even need to compress that much. It only needs to compress m instances of size n to m log n bit strings. Right? In particular, you could keep like log n bits of information per input. And he said even this is good enough. And he showed that if you have a compressing reduction for OR of L with these parameters, then in fact L is contained in SDK. Right? SDK is this class of languages that I mentioned at the beginning. And this was really the starting point of our work. We started with these two observations. The first was that Drucker's results carry over very easily to lossy reductions. And the second was that SDK, right? So he showed that this implies that L is contained in SDK. And as I said in the beginning, being in SDK is a sufficient condition to be used together with average case hardness to get one-way functions. So Drucker's result immediately tells you that if you have a language which is average case hard and has reductions like this that are only somewhat lossy, then you can put these two things together to get one-way functions. And we asked, okay, can you do more than this? Can you do more from lossy reductions than what you can just do with SDK, right? And it turns out you could. In particular, by assuming something slightly stronger about these reductions, by asking that, in particular, the reduction goes to L itself, from OR of L to L itself, and it's slightly more lossy than what Drucker could do, we could show that this is sufficient structure to use with worst case hardness rather than average case hardness to get one-way functions. Right? And this is done in two parts, which are quite telling. The first one is the earlier corollary that L is in SDK that Drucker showed. And the second is what I would think is the more interesting thing, which is, again, something that follows from lemmas that Drucker proved, which say that you can use this kind of self-lossy reduction to do a kind of worst case to average case reduction from the language to itself. Right? So in particular, you can start with L being worst case hard and having this reduction to get the conclusion that L is one-sided average case hard. I'll tell you what this is in a minute. So once you have these two things, you need to put them together to get the one-way function. And this you can do using sort of known techniques that you could also have used to show that SDK and normal average case hardness gives you one-way function. Right? So I'm going to tell you a little bit more about this step because this really shows you how these lossy reductions are useful. Right? So let's say what you start with is this, right? You have a reduction R, which is like a lossy reduction for R of some language L to itself. Right? So in particular, you have these properties that it's a correct reduction. Assume for now that it's perfect, right? So it says if there is some input which is in the language, then the output is in the language, and also that it loses information. Right? What we want to sort of exploit is this idea that if there is this information loss, then the output cannot remember too much about all of its inputs. It has to forget a lot of things about some of its inputs, right? And this was formalized by Drucker in this beautiful lemma that he called the disgracing distribution lemma, which says basically this, okay? He says if you have such a reduction, then there is a distribution that is supported entirely in the complement of this L, right? Such that you take any input X that is not in L, right? And you do the following process. You take a random input to the reduction and put your X there, right? Pick some random I, set Xi to be equal to X, and sample the other inputs from this distribution D, right? And then you look at the output Y. What Drucker showed was that there is one distribution such that it doesn't matter what X you take that is in L bar, you get the same, almost the same distribution on Y. Right? So essentially saying that this Y is forgetting what this X was as long as it was contained in L bar. Right? And this is the core of everything. This is like what we are going to use to show our average case reduction, right? And it's going to be quite simple. So what we are going to do is we take the distribution of Y that comes out of this, call it D0, right? And you make the following two observations. First, since Y was generated by picking only inputs that were in L bar, Y is also contained in L bar, right? Because the reduction is correct. Like all the inputs are in L bar, so output has to be in L bar. On the other hand, if you do the same process with an X that is contained in L rather than not in L, then Y has to be contained in L, again by the correctness of the reduction, right? So you put these two things together with the assumption that L is worst case hard, and it immediately tells you that for any polynomial time algorithm A that is trying to, for any polynomial time algorithm A, there is some distribution over instances in L that it cannot distinguish from D0, right? Because if it were the case that it can distinguish it can distinguish all distributions in L from D0, then you could use it to solve L in the worst case by just passing your input through this reduction and asking it to distinguish. Right? And this is why we call it one-sided, because one of the distributions that it's distinguishing between is fixed, but the other is not. Like for every polynomial time algorithm, there is some distribution that it cannot distinguish from this fixed distribution. Right? And this is what we call one-sided average case hardness. And this we show then how you can put this together with SDK to get one-way functions. And this gives us this theorem that you can use lossy reductions for R, lossy self-reductions for R to get one-way functions with worst case hardness. We also show using somewhat, taking slightly different route, but vaguely similar ideas, but different in details, that you can make certain trade-offs in these hypotheses. In particular, if you can do reduction for majority, which is harder, then you don't have to do a self-reduction. You can just use any other language with the same lossiness parameters, and you can still get one-way functions along with worst case hardness. And then we also show that if you impose much stronger conditions on your reduction, that it is perfect and not have any error, then you can also relax the amount of lossiness you require. Right? And finally, we also show that if you have better hardness, if you have one-sided average case hardness plus some other conditions, then you can, along with some perfect lossy reductions, perfect compressing reductions, you can get something much better. You can get collision-resistant hash functions. And that's all I have time to say now. And this is what we do, right? We have these new sufficient conditions for hardness being useful that goes through these concepts of lossy reductions and and one side at Garbage case hardness. There are lots of questions that this raises. I'll mention a few of these now. One thing that we tried but weren't quite able to do is try to get lossy reductions for languages that we do not know that we believe to be hard, right? Because that would be, that's sort of the application we were hoping for, that maybe we could take a language that we believe to be hard, that we don't know how to use for cryptography, and then we could show some kind of lossy reduction that will make it useful for cryptography. There are some candidates I can tell you about that I have in mind, but I can talk to you later about this. And then another question is whether you can use this in place of randomized encodings, because like I said, this is like a weakening of randomized encodings. Can you use it in some applications profitably? And finally, I don't have much to say about this. This seems like a cool thing to me, if you can come up with some computational notion of information loss. Yeah, that's it.
Okay, thank you, Prashant. Okay, so the next talk is on the cryptographic hardness of local search by Nir Bitansky, aka me, and Idan Gerichter, my student, who unfortunately couldn't make it here. So I'm going to take off my session chair hat and put on my speaker hat, and I'll give the talk. Yeah, well, without the hat, I guess. So local search is a pretty common approach to optimization problems. We basically define some notion of neighboring between solutions. You start off with some possibly bad solution, and you repeatedly improve your solution until you can no longer do it. You've reached sort of a local optimum, and you hope for the best. And as you know, there are many algorithms that sort of apply this rule, like the simplex algorithm or gradient descent. And in some cases, local optimum may be all that you actually want. But in general, you want it to be of good quality, ideally as the global optimum, and also get to it pretty fast. And it turns out that this approach works quite well empirically for many problems, including problems that are NP-hard in the worst case. And this sort of interesting situation led Johnson, Papadimitriou, and Yannakakis to a systematic study of the complexity of local search. And they defined a class known as PLS, which includes all search problems where you can efficiently verify local optima. And the first thing that we sort of noted is that this class is a subclass of total search problems, TFNP, which in particular means that it can't be too hard. It cannot include NP-hard problem unless the hierarchy collapses. But nevertheless, what we did show, and many subsequent work showed, is that this class does have a variety of complete problems from different areas like combinatorics or game theory. Now, while these complete problems are not something that we know how to solve in the worst case, as I told you, empirically, in many cases, they seem to be easy. So it would be great if we can get additional evidence of hardness for this class, and in particular have an explicit way of generating hard instances. And the place we're going to look for those hard instances is cryptography. And why cryptography? Well, first, because I'm a cryptographer, where else would I look? But beyond that, cryptographic problems really seem to sort of live in the same area as PLS. We believe that they're hard, but we're not NP-hard. So it would be great if we can reduce them to PLS. And indeed, this has been done but so far under quite non-standard assumptions. And to be fair, these strong assumptions are not only used to show PLS hardness, they actually show hardness in the intersection of PLS and p-pod, which is well known for its characterization by the Nash equilibria problem. Okay, so with this in mind, let me tell you what our results are. So the first result is PLS hardness based on standard cryptographic assumptions, specifically from a Diffie-Hellman type problem in bilinear groups, which is something standard in cryptography that we use all the time, and the exponential time hypothesis. And there's sort of a trade-off between the two. You don't have to assume the exponential time hypothesis. You can assume something weaker at the account of assuming that this Diffie-Hellman problem resists a stronger attacker. The second result is PLS hardness relative to a random oracle. And here, there was actually a result known also in the intersection with p-pod, but it assumed one-way functions. And one-way function is something that usually we can get from random oracles, but here the result doesn't quite relativize. And more than that, it's somewhat complex. It uses PCP-based techniques or sum check techniques. And the result that we show in the random oracle model is unconditional, and it's also relatively simple, dare I say, implementable. And another sort of nice bonus feature of this result is that you also get a problem that is hard to parallelize, in the sense that you can sequentially solve it in some time t, but not less than that even if you're given much more than t parallel processors. Okay. So in the rest of the time that I have, let me sort of give you a taste of the concepts and ideas that go into this construction. So for this, we need to have some concrete PLS hard problem in mind, and we're going to think about a canonical local optima problem. And here we have a space of solutions that we're going to identify with n-bit strings, and the input is going to be two circuits. The first circuit sort of assigns every solution a neighbor solution, and the second circuit simply tells us what is the value of every solution. And our goal is to find a local optimum in the sense that its neighbor is not strictly better. Okay, so this is a PLS complete problem, and how are we going to get such a hard instance? So here's a natural approach, something you could try to do. Let's try to embed a hard problem in this sort of graph. So take a hard search problem in p-space that you can solve in exponential time by a p-space machine, let's say for simplicity time 2 to the n. And think about your solutions or nodes as the states of this computation. And here the neighbor of every state will simply be the next state in the computation, and the value of state I is simply going to be I. And in the corresponding graph, we're going to have a single maximum. It's going to be a global maximum. And if you manage to find this maximum, then it sort of encodes the final state of the computation, which gives us a solution for our hard problem. Now, there's one thing that sort of goes wrong with this approach, which is we cannot really verify, we cannot efficiently verify that states are valid, that we're not sort of bogus. In particular, someone could come up with a bogus final state trying to solve this problem. And even if we assume that the problem is in NP, then this sort of verification problem will propagate backwards and will end up creating useless local optima. So how can you solve this? So here comes to the picture a concept called incrementally-verifiable computation, which is something introduced by Paul Valiant. And it's basically a compiler that lets you take a given computation and turn it into a new computation that, together with every state, also spits out a proof of correctness for the state. And these proofs are sort of locally verifiable and computable. You can increment one proof to the next proof. And the soundness guarantee is that it's computationally hard to find proofs for bogus states. Now, if you have this object, then it seems to help us a lot, because now you can sort of verify bogus states. You can assign them a minimal value and sort of throw them away from our picture. But as it turns out, this is still not quite enough. And the problem is that even correct states may have different valid proofs. You might be able to sort of perturb a proof that was generated by this incremental procedure and get a different valid proofs. And for proofs that weren't generated by this incremental procedure, we don't have any completeness guarantee. In particular, we may be able to find such a proof, and then when we try to increment it, we'll get an invalid proof. And this will sort of cause a useless local optima. So how do you solve this? So what previous work did is really rely on a stronger form of IVC, where proofs are guaranteed to be unique. Okay, so every valid state has a unique valid proof. And the downside is that so far we only know how to do this based on non-standard assumption. But then again, it also leads to stronger hardness, even hardness in PPAD. And the main observation behind our results is that if you restrict attention to PLS, then you can actually trade this uniqueness property with a natural property that we call incremental completeness, which essentially says that valid proofs will always be incremented to valid proofs, regardless of whether they were generated by this incremental computation or not. And this will be sufficient to show PLS hardness. In particular, we'll just get many parallel copies of the original graph, where we know that every maximum sort of encodes the final states and a solution to our hard problem. And what we demonstrate is that incremental completeness is indeed something that is easier to obtain than uniqueness. So for once, if you sort of rely on the common approach to get incrementally verifiable computation in the standard model, which is recursive composition of succinct proofs, then incremental completeness is something that you almost always get for free. And this is how we derive our results in the standard model from existing works. And we also show how you can use incremental completeness to obtain hardness in the random oracle model. And this is based on a notion of incremental proofs of work, which is something that was born in the context of blockchains. And this object doesn't quite give general IVC compilers. Rather, it's a specific incrementally verifiable computation, but this is enough for PLS. And we show that existing constructions are actually incrementally complete with perhaps slight changes. And as a bonus, these constructions are also hard to parallelize. In the blockchain context, this is important. Here, it's a bonus. Okay, so this is all I can tell you about the result in this in the time frame that we have. So let me leave you with some food for thought. So so far, all the cryptographic evidence that we've seen for hardness in PLS or PPAD has been based on this very strong object of incrementally verifiable computation that you can do a lot of things with in crypto. And the question is whether this is an overkill. My guess would be that yes, and that it should be possible to actually prove such hardness directly based on traditional assumptions like factoring or lattice-based problems. And in fact, this is true for slightly higher complexity classes. Okay, so think about it, and this is all that I'm going to tell you. Thanks. So back to my hat as session chair. Any questions to the speaker? Okay, so thanks. So our next talk is going to be about, let me read this correctly, computationally data independent memory hard functions, and Samson is going to be given the talk.
Okay, so yeah, as Nir said, this work will be on computationally data-independent memory hard functions. And this is joint work with Jeremiah Blackie and Mohammed Hussain Mary, who are both in the audience. Okay, so let's start by breaking down this title into its components. So a memory hard function is a function that requires a lot of memory to compute. So there are different metrics that we can use to evaluate how much memory a function will use in its computation. But the metric that we'll use in our talk is going to be the cumulative memory complexity, or CC. So the cumulative memory complexity is just the amount of memory a function uses across the whole time of its computation. So if you take a curve, it's just going to be the area under the curve. So cumulative memory complexity enjoys some properties that other metrics may not have. For example, it amortizes nicely. So if you take the computation of multiple instances, then the cost is going to be the cost of a single instance times the number of computational instances you do. So for this reason, CC is often used when evaluating how good a function is in the context of password hashing, when we want to discourage an adversary from making a large number of parallel guesses at the same time, but you want also an honest user to be able to log in quickly. So broadly speaking, a memory hard function can be categorized into two different classes. In a data-independent memory hard function, or IMHF, the memory access pattern for the evaluation algorithm is static, so it's going to be the same regardless of the input. So for example, let's look at the memory access pattern for f of x. Then let's suppose we access this location first, followed by this location, this third location in RAM, and so forth. Now, let's suppose we consider the evaluation of a different input, y. Since we have an IMHF, it's actually going to be the same memory access pattern. On the other hand, for a data-dependent memory hard function, or a DMHF, the memory access pattern is going to be dynamic, so it depends on the input. So let's say that we have the same memory access pattern for f of x, but then when we look at f of y, the algorithm computing this will look at different locations in RAM. Okay, so because an IMHF has the same memory access pattern across different inputs, then it will resist side channel attacks, meaning that someone eavesdropping and looking at the memory access patterns won't really learn anything about the input. But on the other hand, it's known that the CC of any IMHF is subquadratic. Sorry, when I say subquadratic, I mean subquadratic n, where n is the sequential runtime. On the other hand, for a DMHF, there exist constructions with optimal CC, which is quadratic. I can show this later. But they're vulnerable to side channel attacks because their memory access patterns depend on the input. So a natural question to ask is whether we can get rid of these trade-offs and design a function that has both optimal CC and resists side channel attacks. So to do this, we define a concept called computationally independent memory hard function, or CIMHF. Intuitively, in a CIMHF, the attacker cannot distinguish between a memory access patterns for two different inputs. We formalize this in a game where the attacker can compute pre-computation. So this intuitively means that the attacker is not going to be able to do some kind of side channel attack either. So the naive approach would be to take a DMHF with maximal CC and hide the memory access patterns using something like oblivious RAM. So this would give a runtime of n log n, because oblivious RAM is known to have a log n multiplicative overhead time. But on the other hand, the memory cost will still be n squared, so the effective memory cost is still going to be subquadratic in the new runtime. So instead, we construct a family of these k-restricted dynamic graphs. I'll just define that later. Where for any k that is polynomial in the runtime n, we'll actually have an optimal CC. We also define this property called amenable to shuffling, and we show a CIMHF construction for these graphs that are amenable to shuffling. So these two combined implies that there exists a family of CMHFs with maximal CC. We also show that for small k, it is impossible to get anything with optimal CC. So our results essentially characterize the spectrum of k-restricted graphs. We do require some assumptions. So the first thing we assume is that the evaluation algorithm has some small data structure that the attacker cannot see. So for example, consider like this two-tiered memory architecture where attackers can see read-write access patterns to RAM, but not to cache. So it's not necessary to assume that the data structure is small, but if it's large and it's hidden from the attacker, then we essentially get ORAM for free, so it trivializes the problem. Okay, so before I begin like the technical part of my talk, let me just say that memory hard functions can be viewed in this following sense. So let's suppose we have an underlying DAG G and a hash function H. Let's also suppose that each of the nodes on this graph have some kind of label. So the label of the first node is going to be H of the password, and the label of the last node is going to be the hash. So for the interior nodes, we'll say that the label of a node is H applied to the concatenation of the labels of the parents of the nodes. So for example, L3 is H of L1 and L2 because node 3 has parents 1 and 2. So one can notice that it's going to be difficult to compute a label of a node if you don't have the labels of its parents. Okay, so we can characterize this dependency by looking at DMHFs and IMHFs. So in a DMHF, the labels of the nodes, the dependency graph, aren't known until the previous label is known. So for example, let's look at this DMHF called scrypt. And let's suppose that we've computed the first 5 labels. Now we can finally look at the incoming edge for node 6, and then we can compute label 6. Then we can find the incoming edge for label 7 and compute label 7. Then we can look at 8 and so forth. So at the end, the entire graph is finally revealed to us and we know what it looks like. But we can't do this until the very end. On the other hand, from IMHF, the graph is static, which means that the edges are known beforehand and they don't change depending on the input. So now we can talk about this definition of k-restricted dynamic graphs. So in this DMHF that we talked about earlier, a potential parent of each of the nodes in the last 5 nodes has to come from the first 5 nodes. So it's like a 5-restricted dynamic graph. But more generally, in a DMHF, it can be up to n. So the number of potential parents could be linear. But in IMHF, such as the one in the example below, k equals 2. Okay, so we give a description and a construction of maximally hard k-restricted dynamic graphs. So we'll take some graph on n nodes. I'll tell you this in a bit. And then we extend it with n more nodes so that it's a path of length 2n. So we're going to take the first n nodes, and we're going to split them into blocks of size k each. So each block is going to have k labels, and we're going to generate edges from these blocks in round-robin fashion. So we look at node n plus 1, and we're going to generate an incoming edge from block 1 uniformly at random. Then we're going to look at n plus 2, generate an edge from block 2 uniformly at random, and so forth. So notice that for any n over k consecutive nodes, the potential parents are all n nodes in the first n nodes. So if one wants to compute the labels of some of these nodes, one can look at strategies that follow 2 extreme ideas. One can either keep labels on nodes 1 through n, or they can recompute some of the labels when they're necessary. So if you follow the first strategy, then you're going to keep n nodes, and you're going to do this for n steps, which incurs a cost of n squared. On the other hand, if an attacker does the second strategy, it's possible that they might have a smaller cost. So we really want to design the graph on nodes 1 to n to discourage the second strategy. We do this using some constructions called Greats graphs and superconcentrators. And the idea is that for these graphs, one needs to compute a large fraction of the labels from nodes 1 to n. So this is going to be prohibitively expensive. You have to do this a large number of times, and thus an attacker will commit to the first strategy. We also showed that our construction is amenable to shuffling. And a graph that's amenable to shuffling, we show yields a sequential evaluation algorithm in linear time that's also a CIMHF. So this implies a CIMHF construction that is optimal in CC. We also give an attack on k-restricted graphs. And the idea is the following. So previously, we said that there are two strategies that the attacker could follow. In the first strategy, the cost is going to be n squared. But in the second strategy, the cost was prohibitively expensive in our previous example because we made the graph really difficult to compute. But if k is small, it's no longer possible. Namely, we give an attack that follows some elements of AB16. And what they do is compute a small number of labels, keep these labels around in memory, and then compute the larger set of labels when they're necessary, because these labels are chosen in some strategic locations. So this attack is explicit. Using Valiant's lemma, we can explicitly compute the labels that we should keep, and this will give an attack that has subquadratic CC. So in summary, we construct a family of k-restricted dynamic graphs with optimal CC for large k. And for small k, we show that there exist no constructions with quadratic CC. And this demonstrates like a nice phase transition for k-restricted graphs. Okay, so there are actually a number of interesting directions that I would like to consider in the future. One possibility is to fully characterize and tighten the bounds for the spectrum of k-restricted dynamic graphs. Another interesting area to pursue is whether or not we can get optimal CIMHFs without cache hard key assumptions. Finally, for those familiar, we would like to show pebbling reductions for DMHFs instead of just IMHFs. That's all. Thanks.
Okay, so we're slightly behind schedule, so let's take questions offline. Thank you, Samson. Yeah, you can clap again. So the last talk of the session is going to be about separating two-round secure computation from oblivious transfer, and James is going to be giving the talk.
Yeah, so this time I'll be speaking in place of Sanjam about this work authored by Benny, Zvika, Sanjam, Yuval, and Akshay. Okay, so, well, first let's define secure MPC. So yeah, in the setting we have a bunch of parties, a bunch of people. They each have their own private input, xi. And they're interested in computing some joint function f on all of their inputs. Okay, so they can all communicate among each other. And for correctness, we want to say that at the end of this communication, they all learn the value of f applied to their joint inputs. For security, we want to say that if you have take any set of parties, any set of adversarial parties, in this case x2, x4, x5, and x6. We want to say that after participating in this interaction, they don't learn anything about x1 or x3, except for the value of f on their joint inputs. Okay. So some background on MPC. It was really introduced in the 80s. So Yao in 86 introduced it in the two-party setting. And then Goldreich, Macaulay, and Widgerson in 87 generalized it to the multi-party setting. And this is like a very important and central primitive in cryptography, really because like most cryptographic tasks that you may want to do can actually be cast as a special case of general MPC. And so, yeah, as I mentioned, the results that Yao gave in the 80s and GMW, they basically showed that like any function that you want to compute, any efficient function, can also be computed securely. Okay, and so yeah, so does this like settle the question of MPC? Not really, because like the constructions that they give are quite inefficient, and they can really just be seen as feasibility results. Okay, so what do I mean by inefficient? I guess you can measure the security of MPC or the efficiency of MPC protocols along a number of different axes. So one is like the number of rounds of communication. Okay, and so this is pretty important when in high latency networks. So another thing is like how much are these parties actually computing beyond what they would have needed to just to insecurely compute the function f. And so this is often highly correlated with like the type of cryptographic assumptions that are used. And in particular, it's correlated with like how these assumptions are being used. Namely, are they used in a black box or a non-black box way? So if they're used in a non-black box way, that means somehow the protocol is taking advantage of the circuit implementing this primitive. And this often can lead to very inefficient constructions. So this is highly undesirable. Okay, so a third thing would be communication cost, like how much data is actually being exchanged between these parties during the protocol. And this would be crucial for bandwidth constrained scenarios. And really this paper is more interested in these first two. So so starting with the round complexity, it's been known for a while, at least it's been folklore, that at least two rounds are necessary for securely computing certain functionalities. And this means, in particular, that this simple two-party functionality called oblivious transfer is going to be a necessary cryptographic assumption for general MPC, since oblivious transfer is it's a special case of MPC. But actually, in Yao's initial work in '86, he was able to show that, in fact, two-round OT is actually sufficient for general two-party computation. So he showed that two-round OT implies two-round general two-party computation. And much later, but actually pretty recently, there were some very nice works that gave a similar result, but in the more general multi-party setting. Okay, so they showed that in fact two-round OT is also sufficient to securely compute any multi-party functionality. However, the big difference between these results is in how OT is actually used. So in the multi-party setting, these works make non-black box use of OT, while Yao in the 80s showed that two-party computation can be based on just black box use of two-round OT. Okay, so the question that motivated this work is like in the multi-party setting, is this non-black box use of OT actually necessary? And well, the main result is basically they show that this non-black box use is indeed necessary. And so in particular, what this is saying, it's like in the setting of two-round protocols, there exists some three-party functionality such that no secure protocol for computing this three-party functionality exists that only makes black box use of two-round OT. Okay. And a corollary of this that follows from Yao's work is that, well, this functionality, this three-party functionality, cannot be computed securely, making use of black box use of any two-party functionality, because Yao showed that in a black box way, two-round OT implies general two-round 2PC. Okay. Okay. So. Yeah, in the remaining time, I can basically give some very brief overview of how the proof of this main theorem works. And indeed, the three-party functionality that's used to prove this is quite a natural example. And so this is what it is. It's called external AND. So we have three parties. One party gets no inputs. Each of the other parties gets a bit. And they all want to learn the AND of these bits. Okay. So, well, they show in this work that this cannot be done securely using just black box use of 2-round OT. So, well, suppose for a contradiction that you can. So suppose there exists a protocol that makes use of black box use of OT. So you can kind of imagine, for the sake of a proof, that like these three parties have like access to some oracle that's like allowing them to compute OTs. Okay. Now the first step is to transform this 3-party protocol to a 2-party protocol for computing AND. With this like special property that's called a publicly decodable transcript. Okay, so they convert it to this 2-party protocol such that any external like third party after these guys compute, any external person can come and like just look at the transcript, and from that transcript they can actually learn the result of x1 and x2. And so this transformation is shown using some standard player emulation techniques. Basically, like the random state of the previous third party is like simulated in this transcript. So, okay. So now they have this 2-party protocol for computing AND with this publicly decodable transcript property. And really, the bulk of the work is to transform this protocol. Recall, we're still making use of this OT oracle. The bulk of the work is to transform the protocol by adding rounds, but basically getting rid of the OT oracle and replacing it with a random oracle. And so they can show this. They managed to show this transformation to this now multi-round protocol that just uses a random oracle and still securely computes this AND functionality. And so, in fact, it was shown in previous work that such a protocol is actually impossible to achieve. Okay, so this completes their proof, and so this is where the bulk of the proof is, and I would encourage people to look at the paper for how this part actually works. Okay, so I can conclude. The question that motivated this work was, okay, is it possible to realize general, secure, 2-round multi-party computation using just black box use of 2-round OT? And they show that this is impossible. So this actually brings up the question, well, okay, so if 2-round OT is not black box sufficient, what primitive is black box sufficient for 2-round MPC? And they show a particular 4-party functionality that turns out to be sufficient for a black box construction of general MPC. And so this leaves open the question, so what about 3-party functionalities? What is the status there? And they show here that, well, whether there exists a 3-party functionality that suffices in a black box manner to build a secure 2-round MPC is closely related to this long-standing open question that's basically like, do there exist statistical randomized encodings that are just use degree 2 polynomials? So this has remained open for a while, and they show that this is settling this question of 3 parties is related to this question. So thanks.
Okay, any questions? We have time maybe for one. Okay, so let's thank James and all the other speakers in the session. And now we have a short break, and